Swayam Prabha. Digital India. Educated India.
Welcome back. So, today I am going to digress a bit, and we were doing magnetic circuits. Now, I am going to digress a bit and look into sinusoids. The reason for looking into sinusoids is that our voltage supply all over the grid, the residences, everywhere, factories, railway stations, cinema halls, whatever, are basically sinusoids. They are of the form Bm sine of omega t plus phi, and in India the frequency that we are having for our supply is 50 hertz. So, it is 2 pi into 50 equal to 100 pi radians per second. So, to just get the picture back to you, this is a sinusoid, a simple sine wave, right. And if you look at this, this is a cosine wave. Now, of course, they are of, I have deliberately, I am going to rub it off again, and they were of different amplitudes. And if this axis x, the t equal to 0 line, if it was displaced, let us say somewhere here, then I would get a waveform at t equal to 0, which is of sine of, let us say this amplitude is a. So, I will get it as a sine of omega t minus phi. At t equal to 0, the value is minus of a of phi, this angle being the angle phi. So, what I am trying to sort of say here is that this sinusoid has two main attributes. One is the amplitude or the peak value, and of course, and second is the phi, which is the phase angle, the phi which is the phase angle, and of course, third one is frequency. But because our grid runs at either at 50 hertz in India, 60 hertz in North America, and 50 hertz in Europe as well. So, therefore, the frequency is practically constant. So, our voltages, and as a consequence of it the currents also turn out to be sinusoids, and these sinusoids, therefore, most of the electrical engineering is in some sense analysis of sinusoids. At power engineering is actually analysis of sinusoids at constant frequency, and this is usually done by something which is known as a phasor or a phasor analysis. Now, I am going to digress a bit. This was not in my initial plan, but a thought may have come to your mind that why is it that we are having voltage waveforms as sinusoids? And one simple reason is just to show it by, of course, DC is also possible to develop a DC waveform, but the basic construct, if you look at it, geometry, if you look at the geometry of a basic generator, very simple generator, you would see that actually by naturally it generates sinusoids. There are some other mathematical advantages also that I will discuss a bit more as I discuss sinusoids in more detail. But let us say that this is one turn coil, one turn means you can even have n turns here, but concentrated, a concentrated coil here. Let us call this, since there is only A phase, let us call this as A dash. Right now I am only looking at single phase, 3 phase we will come to a bit later on, and this is the way the flux lines will pass this is a ferromagnetic structure to ease the development and flow of magnetic flux. This air gap which I have shown here is actually very small. For my ease of drawing, I have drawn a big air gap, but it just practically its purpose is to avoid friction, and really there is nothing more than that we want to do. Now, let us say that this is coupled to some mechanical system. Okay. This is coupled to some mechanical system which causes it to rotate at 50 cycles per second, which causes it to rotate at 50 cycles per second, which in honor of hertz we call it as a 50 hertz rotation. Now, if this EMF for the time being I am going to this to for the sake of description. So, let us say that this A, right now the direction of the coil S and the direction of the flux B, okay, the direction of the flux phi which is created right now is is 0 degree. So, they are both the flux waveform and the S waveform are collinear, are in the same direction, and actually you could think of it as a much bigger you could think of it as a much wider structure, and if the air gap is uniform, the radial air gap is uniform, let us say this is pi by 2, then this is going to be minus pi by 2, my default direction of rotation and angle measurement is anti-clockwise. So, the B structure that I am going to get, the B structure which I am going to get here is so 1, 2, 3. Let us not come out symmetric, let me make it a bit more symmetric, and let me push this a bit to the center. Okay. So, the B structure is going to be 1, 2 and 3, 1, 2 and 3, 1, 2, 3, think yeah, so not what it is, I have to go 6. So 1 2 3 4 5 6, maintain the symmetry here. And so this is going to be 1 2, it will continue like something like this. So the point which I am trying to make here, let me center this figure a bit. So now I can make 1 2 3 4 5 6. So this completes one cycle. Then this will go like this. So the point which I am trying to this is the angle theta which is drawn here. So the point which I am trying to sort of make to you is that this waveform, if you look at it, actually is kind of a is a rectangular kind of a waveform, but in practice actually we taper the pole faces. What are the pole faces? These are the pole faces. This is my pole, and I will have least gap in the center line. I will have least gap at the center line, and as I go further away, I will increase the gap. So, if I do it, I will get a more, in fact, tapered waveform, and in a very ideal kind of a case, you can imagine that this waveform will look as follows. I am going to not draw it overlapping, but I am not going to but actually what I am going to do is draw it a bit separately. So what I am going to get is a waveform which looks like this. There are advantages to making it like a sinusoid, and we will see those advantages as time flies in this course, but with some trick of tapering we can make this waveform look like Bm cos of theta. So this waveform we can make it look like itself, we can make it look like a sinusoid. Alternatively, and I will do this a bit in more detail later on, you can think of this as having a fundamental component at whatever is this diameter at fundamental component and plus harmonics. How will you get this? You will get this by doing Fourier analysis. If you are aware of it, then you would realize that this can be obtained by doing a Fourier analysis. If you are not aware of it, no problem, you just think of it that I can approximate it, just think of it that I can approximate it by a sinusoid like this, and this is only an approximation. So, there would be more terms to make it exact which cancel. For example, you see this excess peak going here over and above it. So, something else has to come in again in a later term to cancel it out, to make approximation closer and closer, and this is exactly what a Fourier analysis would do. So, the Fourier analysis would tell you that this B of t can be written as Bm cos of theta plus more harmonic terms. So, this is called usually the fundamental term, the fundamental space, and this being in space we will call it as the fundamental, and then the other things as, for example, there could be terms like cos of 3 times of theta and so on. In general, if a waveform is periodic, like this has a period of 2 pi, if this has a period of 2 pi, this is pi by 2, this is minus pi by 2, this is exactly one time period, and then this will be pi, and then this will be minus pi. So, this covers the one time period of it. In general, waveforms which are periodic usually shown as f of t, but it could be f of x, it could be since I am talking of theta here, let me write it as f of theta, provided that it is periodic, which means that it is n, in my case it is equal to f of theta is equal to f of theta plus 2 n pi, where n is any integer plus minus 1 plus minus 2 whatever. So, this is a periodic waveform in space. This is a periodic waveform in space. It can be written as a constant A naught or C naught if you want. I will write it as A naught plus sigma A n cos of n omega t, and since here the period is itself 2 pi radians. So, 2 pi by t here corresponds to 2 pi by 2 pi. So, therefore, the fundamental is actually at one value of 1, but in general it will be, I will write it for t itself. This is so standard in the mind. At periodic signal f of t equal to f of t plus n t with fundamental frequency 2 pi by t can be written as a summation of there are some conditions, they are known as Dirichlet's condition for those of you who have learned Fourier series, but most of our practical waveforms meet this, and so I am not sure, there could be more than just third harmonic. So, I will right now just not bother about this whether it is even harmonic or odd harmonic. That analysis will, if required, we will look at it in later on. So, let us not just say that it is only first, third and fifth, but let us just stick to the very basics of the Fourier analysis right now, which says that there will be a DC, a periodic waveform like this will have a DC component, and then a sinusoids like this, and cosinusoids and sinusoids like this, which are at fundamental frequency and then harmonic frequencies. N equal to 1 is fundamental, n equal to 2 is the second harmonic, n equal to 3 is the third harmonic, and so on and so forth. So now if the waveform is like this, if the waveform is like this and A naught is actually the average value of f of t over one cycle. So, minus t by 2 to plus t by 2, then you can see that this value, this area here integrated from this to this. So, if you call this if you call this much part as plus 1, then this will be plus 1, this will be minus 1, this will be minus 1, and so it will cancel out. So, plus a, minus a, minus a, and it will cancel out. So, see, waveforms like this will have 0 average value. So, you will end up when it has a 0 average value like this, because of the nice symmetry here, then you will only get fundamental component. This is the fundamental component plus other harmonics, and since I do not want to go deeper into this, I just am going to say that these harmonics usually are the way I have for example shown here. They reduce, in this case they will reduce in inverse proportion to n, sometimes they can reduce in inverse proportion to n square, whatever. In this case they will reduce in inverse proportion to n, and so as a first approximation, this b of theta could be written as some constant a1 cos of theta plus some constant b1 sin of theta. Now, at theta since this waveform you can geometrically sort of see this is more closely approximated by a cosine wave, is more closely approximated by cosine wave. So, we can actually show that this B 1 in this term will come out to be 0, and therefore, this is basically some sort of B m cos of theta. This is the fundamental component. If you are thinking on how do I evaluate this A n and B n, then again just to jog your memory for those who have done Fourier analysis before, and for those of you who have not done Fourier analysis before, you can multiply this equation by cos n of omega of t. So, f n of t cos n of omega of t, you integrate it from minus t by 2 to plus t by 2, and then look at 2 by t, and that will give you a n. And similarly, when you multiply this multiply this by, let us say, sine of omega of t, sine of n of omega of t, and integrate and then look at it, you will get a term called the B n of t. So, so it is, I mean, to show that B 1 is equal to 0, which I am not right now doing here, is really not a difficult thing to do. Basically, actually it happens that finally I am doing it only, but basically what happens is, I had a waveform like this, right. I had it at 1, I am going to one, 2, 3, 4, So if I am sorry, this should come here. Hmm. 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2, 3, 4, and then so this is my b of t versus b of theta versus theta. Now suppose I take a sine, okay. Let me change the color. So let me take this is pi by 2, remember this is minus pi by 2. So if I take somewhere here is the pi and somewhere here is the minus of pi. So if I take a sine of fundamental frequency, let us say this, I am sorry, and something like this, it should be somewhere here. Then you can see that this area cancels out in the integration that I am going to do for calculating b of 1. I am going to do the calculation of this b of theta into sine of theta d theta from minus pi to plus pi, and the time period here is 1 by 2 pi. So, I am going to do this from 1 by 2 pi to this. So, this area is actually why is this area cancelling out? Is it sort of clear to you why that is happening? Look at it carefully. Here this side the sign is positive, this waveform for the time being let us say that this is plus 1 value, just for the sake of simplicity. So, then this is just a integration of the sign, this is just integration of sign in this particular area. Now, this side let us come onto this side, again in this is plus 1 only, and this plus 1 is multiplied by, in my Bn sine of theta, this plus 1 is multiplied by this. So, it becomes negative, and so the area that I am going to accumulate in this part is only this much. So, these two areas are equal and opposite by symmetry, and in sine they are opposite and otherwise they are equal. So, therefore, when you have done the integration from this part to this part, these areas have cancelled out and given you a 0. Now, come to this particular remaining part of it. So, look at this particular area. Here the area is actually again positive because this is minus 1 and this one is negative. So, this is exactly same area as this, but it is actually positive. And here this area, the area which is represented here is actually negative, because this term which is positive are actually multiplied by negative minus 1 here. So, they give you a negative area here, this gives you positive area exactly same thing, and this gives you that positive area, and this gives you the negative area. So, and these all areas are equal. So, the total sum of the negative areas is equal to total sum of the positive areas, and therefore, the B1 turns out to be 0. So, this is why I said that the fundamental will this can be approximated simply by as a first approximation, and I am not going into harmonics, not too early to dive into harmonics. As a first approximation, this could be approximated as something like Bm cos of theta, where the Bm will be calculated from the formula of A1 that we have written somewhere. Where have we written that formula? This is the Bn, and copy paste, yeah. So here the formula for A1 is basically will give you the value of Bm. We will not calculate it, we are not trying to really too much do analysis of it. I have sort of digressed a bit into it, but it will help, no problem. It will help. These concepts will build on as we go forward. So, what I am saying now is that as an approximation, B of theta can be thought of as Bm cos of theta. This is the thing that I have now, the flux which is this is the approximation of this. Now, the next thing is, what is the flux which is enclosed by the coil? If you want to calculate the EMF which is generated, which Faraday's laws say that it is minus n d phi by dt, then the question is, what is phi of t? And to answer this question now here, first of all we have to take Bm cos of theta, this is the, and then take a small strip, this so assume that this radius is r, okay, somewhere at the center line. Actually you can extend it if you want to somewhere here, but let us take this radius as this and a small d theta. So a small d theta. So then this arc will become r times of d theta. So that arc will become r times of the d theta, and then this whole structure has a length of L. It is like a cylinder from outside. If this is the top view of it, and then the inside the magnet is also kind of sitting in a cylindrical kind of a fashion with a depth of L. So therefore, you will have to multiply it by L, and this will become your d of phi, the flux. And so if you want to actually calculate the flux, what should you do? You should integrate it from minus pi by 2 to plus pi by 2. You should go from start from here, is accumulate the flux, because in all this the flux is moving outward. So, the direction is the same. So, it is a positive accumulation which will keep on happening until you come up to this particular point. Then afterwards the north pole changes to the south pole and the flux starts returning back, the flux then starts returning back. So, you then if you go all the way again up to 2 pi, it will finally become 0. So, if you want to see the flux which is enclosed at this point of time, then it is Bm cos of theta r theta d theta and taken from minus pi by 2 to plus pi by 2, which is equal to, and then L. So, Bm L r integral of cos of theta d theta from minus pi by 2 to plus pi by 2, and differential of sin of theta is cos of theta. So, integral of cos of theta is going to be sin of theta, and this taken from plus pi by 2 to minus pi by 2 will give you Bm 2 L r. This I will call as the maximum flux which is enclosed by the it is the maximum flux which is enclosed by these turns on the, these turns are where? Turns are on the stator, and what, where is my magnet? The magnet is in my is on my rotor. Now, these are, now the magnet is rotating. Now, we are rotating the magnet. So, because of that this direction of ds which is associated with the turns, this is with the of the coil, or the which is associated with the coil is fixed, but the direction which you can associate with the field with the so when the pole rotates, so the coil axis is always like this, but when the pole, so to say, rotates by an angle theta, then its axis, which is basically the axis of the north south pole, will, or the phi m axis will create an angle of theta with it. And since you look at, to calculate the flux, since you look at B dot ds, this being a surface integral B dot ds, so it is going to be phi m cos of theta. Look, this is actually your original position, right? The north south is, this is my, these are my turns A dash, and originally my magnet or north south pole is like this, and we have a tapered coil so that we can have a sinusoidal approximation of Bm. So, as I move across, so therefore, I can write B as an angle of alpha, where alpha is the angle which I am rotating with respect to this axis, which is fixed for this coil. And so, if I go at an angle alpha, then my B is going to be equal to Bm cos of alpha. This is the sinusoidal distribution that we have created. Now, let us say that this magnet has rotated by theta degrees. So, my magnet is now like this. This is my magnet. It has rotated by an angle of theta. So, what has happened to the how will the flux profile look like now? Now, it will the B will be peaking at the angle of theta, which is shown here. The anti-clockwise direction is the positive angle. So, therefore, here you will be moving on the right hand side, while here you seem to be moving on the left hand side, but actually this is anti-clockwise that you are moving, which is positive, and on the, when you draw it on the plane, you are moving on the right hand side. So, it peaks now at theta, and then it has to reduce and follow a trajectory like this. So, therefore, what should be the appropriate equation to represent it? It should be Bm cos of alpha minus theta. So, really the variable is alpha, which alpha variable is where to see what is happening around the complete circumference here. So, it goes from 0 to 330 degrees. Theta is showing where the magnet's peak is centered right now. So, if you now say, if you look at, if you want to calculate phi of theta, so we want to calculate phi of theta. So, what is it going to be equal to? It is going to be equal to Bm cos of alpha minus theta, then L r d alpha, and alpha always to be integrated from minus pi by 2 to plus pi by 2. Why am I integrating from minus pi by 2 to plus pi by 2? Because minus pi by 2 is this point, plus pi by 2 is this point, and whatever is inside of this is the only thing, is the flux which is linking the coil A dash. And what is my L? Actually my L is, if you look, extend it like this and think of this whole thing like this, then and so the magnets are also, the magnet is also inside like this. So, the magnet also extends in this particular way. So, therefore, this L is the length L, R is your mean, distance here, and the arc that is created is d theta. So, this is actually r d theta, and it has a depth of L, and so L r d theta is your ds. We have seen this. So, what we are now going to do, is we are trying to see when the magnet has moved by an angle theta, what is the flux linking the coil A dash, and we have come to that it is going to be this particular value. So, let us take all the constants out, Bm L r, and integrate cos of theta. Integration of cos is going to be sine. So, it is sine of alpha minus theta, and then put the limits of integration, which is minus plus pi by 2 minus pi by 2. So, this is Bm L r sine of pi by 2 minus theta minus sine of pi by 2 plus of, I am sorry, minus of minus will make it plus. So, it is going to be plus of sine of theta, and so this is going to be equal to 2 Bm L r cos of theta, which is nothing but phi m cos of theta. So, now what is the flux linkage? Number of turns times cos of theta, and so when you do this, and what is theta? Because the magnet is rotating at 50 hertz or at some speed omega. So, therefore, theta will be equal to omega t, and in our case in India it is going to be 2 pi into 50, which is 100 pi radians per second. So, that is what this is going to be. So, therefore, E, which is by Lenz's law d psi by dt, which is equal to minus of d psi by dt, and this minus or plus, I am just right now following the way you did it in 12th class, but this is based upon the sign convention. When I put a minus here, usually I just call it as a generator convention, but we have seen it earlier that just by changing the way we mark the polarities, that is what is marked as E, if it gets reversed polarities, then what you have marked it as minus of E, then it can also be shown to be d psi by dt. So, there is something not very significantly worrisome about it. It is basically a question of sign convention. So, this will now become n phi m will come out as common d by dt of cos of omega of t, which is minus n phi m omega sine of omega of t. So, you come to something very interesting. This this not minus will go away, minus of minus will go away. So, you will get sine of omega of t. So, this can be written as Em sine of omega of t. This shows you that generation of a sinusoidal waveform is very fundamental to the rotational structure of a generator, and rotational structure is obviously a symmetric proper kind of a structure that you will develop, right. I mean, your cycles also have wheels which are circles, you know. So, the geometry of circle works very well when it comes to rotation, and advantage of rotation is that you want to generate this EMF. This place does not have to go from Mumbai to Nagpur or wherever, it will be in its own generating plant in a small enclosure, and it will keep rotating. There will be some prime mover below which will be just driving it, and it will keep rotating, and because of that on these two coils here, you will generate this sinusoidal waveform. This is also the reason why I did not stop it at just drawing this waveform this much only. I drew it much more because of the fact that when I come from here and circle, I have completed 2 pi. Then I start the next circle, I complete 4 pi rotation, and so on and so forth. So, therefore, this waveform will come like this, again follow like this, go like this, go like this. If you keep rotating, it will keep on rotating like this ad infinitum. Therefore, this waveform that I am getting here is also going to be ad infinitum until I keep rotating. I will keep getting a sinusoidal voltage waveform E of t or E of t like the following. Now, what is this Em? Em is n phi m omega. So, clearly proportional to omega. Higher the speeds of rotation, higher will be the higher the speeds of the rotation, higher will be the EMF. For example, suppose you are in an aircraft where you want to generate the say similar kind of voltages, but your space is really a problem. You could run the same thing at a higher speed. Instead of 50 hertz, you could probably run it at 400 hertz, and then what would happen? You will generate the same voltage with lesser flux. So, that is the trade off. Suppose I want to have a some given value of voltage, say 110 volts or whatever, and I want to make my structure compact. So, I want to reduce the phi m. So, what do I do to reduce, and what is phi m? Phi m is 2 Bm Lr. So, basically if I reduce the phi m means I reduce the L, I reduce the R. So, therefore, the whole thing becomes compact, but suppose I want still to generate the same voltage, then what should I do? I should rotate it at higher speed. So, that is why, you know, if you go in aircrafts, the supply frequency will be different from what you will see it on ground, and if you go and so on. Now, I do not want to digress again into something else. So, let me come back to this. Em is equal to n phi m omega, which I can again write it as 2 pi n phi m f equal to E m, and usually we need to worry about the root mean square value. We need to worry about root mean square value. What is root mean square value of a waveform? If the periodic waveform is f t equal to f of t plus n t, then if I go from minus t by 2 to 2, and if I look at f square of t, because see with sinusoids, whether they are sines or cosines, the average value is 0. So, you want to get a handle on it, and we will have more about these RMS values. Then you should, the next interesting thing is square it up, so that all the negatives are also positives, and then add all those values, which for a continuous function will amount to integration, and then look at the square root of it, and then this is called as the root mean square value. And this FRMS for a sinusoid, of value say bm or phi m, for value of phi m, the RMS value, the root mean square value is going to be phi m by root 2. Now, why this root 2 is important, I will just illustrate to you. Suppose I had a sinusoidal voltage supply and I had connected it to a resistor, which is a dissipative element. So, then I of t will be Vm sin of omega of t, the voltage supply by R, and the power P of t, which is V of t times of I of t, will be then Vm square sin square omega t by R, and then I am interested in average value of the power, the resistor that it dissipates in one cycle. So, I go from minus t to plus t, 1 by 2 t, minus t by 2 to plus t by 2, 1 by t, p of t, d of t, and if you simplify this, it is going to be V m square by R minus t by 2 to plus t by 2 sin square omega t dt by 1 by t, and you can do this as V m square by R. If I am sorry, this is minus t by 2 to plus t by 2, and if you do this, multiply this by omega on both sides, then it is basically from now minus pi to plus pi, and this will be V m square, and omega t is 2 pi. So, therefore, 2 pi by R, and sin square theta is 1 minus so 1 minus 2 sin square theta is equal to cos of 2 theta. So, therefore, 1 minus cos of 2 theta by 2 times of the integration d theta from minus pi to plus pi, and integration of cos 2 theta, this I leave it to you to check it out, from minus pi to plus pi is going to be 0. So, and the first term, when you integrate it, this with respect to d theta is theta, and then when you integrate it from plus pi to minus pi, then it will exactly be equal to 2 pi, and that 2 pi is going to cancel out with this. So, therefore, this whole thing is going to be V m square by 2 of R, which can be written as V m by root 2 into V m by root 2 by R, and this is actually V RMS into I RMS. So, therefore, this RMS value is very fundamental to us, and this RMS value is very fundamental to us, and this EM, the n phi m omega, E of m, the peak voltage, which is n phi m omega, is this is so. So, if you look at the RMS value of the voltage, then it is going to be, this is usually the nameplate ratings always specify RMS values. So, therefore, this is going to be n phi m by root 2, which is 2 pi by root 2 into n phi m f, which is 4.44 n phi m f. So, this RMS value is related to, this is what the nameplate rating specifies. This is what the nameplate means, whatever on the machine, if whatever is printed, that is called the nameplate. So, the nameplate rating usually specifies this 4.44 n phi m of f. This equation is again a very fundamental equation. You will see this again coming in transformers, you can see it coming in induction motion. So, I did it with something very basic stuff, and this happens again and again and again. So, we will keep this, remember this. RMS value of the voltage is proportional to the peak value of the flux. Peak value of the flux is proportional to peak value of the flux density. It is proportional to area of cross section, which is L times of R. RMS value is proportional to frequency of rotation, which for us is 50 hertz fixed, and RMS value is also proportional to number of turns. So, you want to have more voltage, you can add more turns, proportionately add more, proportionately grow the turns, and the constant factor somewhere here comes out to be 4.44, which is this particular value. So, I think at the end of the day I am going to change a bit of sinusoids to basically a first peak into a synchronous generator. And now all I am going to say, and then I am going to close this class, all I am going to say is, if this is my first phase, how do I get, if this is my first phase, how do I get the other two phases, B and C phases, R, Y, B or A, B, C phases, how do I get that? So, I am going to rub everything here, and I could have as well drawn a new figure, it was too crowded. So, I will actually draw a new figure now. What I want to say is, say this is my stator, now this I am going to mark, this I am going to mark as my R phase winding A dash, then this, remember this is the north south magnet and it is rotating like this. So, suppose 120 degrees later I keep a yellow winding, Y up a yellow winding, I am going to use this color, slightly darker color, this A, another notation used is B dash, A dash, and then color wise R, Y and B. So, then another 120 degrees later I will get a C and somewhere here the C dash windings. So, now whatever voltage is seen by this A dash, whatever voltage is seen by this A dash, same thing will be seen by B dash, but it will happen 120 degrees later. So, therefore, if the 50 hertz time period amounts to 20 milliseconds, then this will happen T by 3 or 20 milliseconds by 3 milliseconds later, and E of C of T will see again the same voltage figure, because the north pole will come exactly in the same alignment with the C dash. After 2 pi by 3 angle has traversed. So, therefore, EC of C will see EM of sine of omega t minus 4 pi by 3. Now, one thing is very clear, if I put a 3 phase winding, I will have a better space utilization of my structure. So, going for multiple phases seems a good idea from the perspective of utilizing the space on the structure properly. There are more fundamental reasons than that, which we will again come back later to, but we could then, somebody may say, why not have 5 phases or 4 phases? Yes, we can have, but the world has standardized now to 3 phases. Whatever extra fundamental benefits that I am going to talk about, you will get it at 3 itself, plus beautiful symmetry at 3. So, 3 has become the world standard on the number of phases today that we have, and this is how we have got our 3 phase AC system. So, I think with this we will take a break for this class today. Thank you.